Welcome to my talk, Passive versus Active Alignment Strategies in Photonic System Assembly. I will try to motivate both strategies, and there will actually be mixtures between the two, and all of them have in common that we do a lot of glass mounting of optical assemblies. I'm from the Optical Interconnection Technology Group at IZM, and we do optical connectivity on several levels and several dimensions. There's a 1D connectivity where you want to have a connection on a single optical channel, like from fiber to fiber. My colleague Boettger already talked about this. There will be a talk next on 2D connectivity, optical interconnectivity, that Julian is going to go into in 2 weeks' time. And today I would like to concentrate on complex 3D structured systems, which can be laser structured and that use active and passive alignment in their assembly. So this is just a quick overview, which already was shown. We have a lot of laboratory space, a lot of labs, and we have been around for quite some time, and we are looking into integrating microelectronics and photonics for new application in 6G for quantum and photonic computing. And I'm going to go into the photonics level, which we can include on panel level in thin glass. The key component of such assemblies is the glass interposer. It has to be structured to contain electrical, thermal, and optical connectivity. So we have two ways to do this. We have a wafer and a panel line, and we can fabricate such complex interposer structures to host photonic chips, to host lenses, optical connections, and basically these components get placed on glass interposers. And if you look into the details of such glass interposers, you see a lot of electrical and thermal connections that are integrated by filling through glass wires with metal. There are also some electrical lines included in this one, and we can also do this type of interconnection on panel levels. And the idea is to go to really large panels, go up to like 510 by 515 millimeters to create even more systems in one run. We have been performing some testing on smaller test panels, and you see there's quite a complexity on these glass, thin glass assemblies. What is not yet included, what will come, is that we include waveguides in such optical interposers, and that we also go for more passive alignment strategies on these. But let me first show you what these thin glass packages really can consist of. You not only have a interposer, but you can add like a spacer and a lid to create an optical interface to the top, doing a Hermetic package for a photonic system in package. Yeah, there you have a electrical and thermal interface to the bottom, an optical interface to the top, and this can either be a free space or fiber coupling. That way, we really look for replacing conventional ways to assemble optical systems like laser diodes, and we try to go for flat panels that are transparent, that have new ways to couple light to the outside. On the right side, we see here a laser diode package that uses the side of the glass box package to couple light to the outside. These panels can be assembled on an active alignment, and we have micrometer accuracy in placing components. And this is a rather small panel, but that's another advantage of panelization. You can choose what format you can produce on. If you go into more complex optical systems, then glass really shows its full potential. And actually, the laser structuring of glass shows many advantages. And this is a rather large system in itself. It's 50 by 100 millimeters and contains some components. You see a lot of free space inside the box, so it could be integrated further. But this is a prototype package, and this was used for testing a new way to assemble optical systems. This rather is you have a light coming into the box. This light is modulated, it's split, and corresponds to 4 fiber Bragg gratings on external fibers. So this is a realization of an optical sensor system, and it uses sequential active alignment and also includes some metallization. This was a really early package that was created, and we got some more ideas doing this. I pointed out that we do active alignment on optical systems. This is the conventional way, I would like to say. That means all light sources that you have in an optical systems are operated, and you can manipulate optical components so you get the best live operation of optical systems. And these are industrial machines that we have available in our clean room, and with typical specs that are known from industry. If we go for really fine alignment, we can go to 5 nanometer resolution and better. We will also work on hexapod stages, which is also a quick way to assemble and test systems. We have been using glass quite a bit, and we found out that is good to have glass mounting structures, and we can have 3D micrometer accurate glass structures that we create by selective laser etching. So you can you can fabricate horizontal coupling benches. You can have any angle or any pitch V-groove arrays for placing optical fibers or integrating lens components. And we can also do some laser shaping or through glass wires in a very controlled manner. One example for a passive alignment assembly stack is this 5 by 5 millimeter vertical coupling stack. In this, an optical fiber gets coupled to from a light source that is included on another glass level. We can produce these systems in panels, and we have created some ways to have clickable systems that we can simply put together in a passive alignment approach. How do we structure these glasses? Here we have ultra short laser pulses that can create 3D structured parts. This is the main process on the machine that we have available at IZM. It's selective laser induced etching. This machine can also do some glass welding, waveguide writing, and actually also some printing of polymers, but I would like to go into the selective laser etching part first. We've created more and more complex assemblies, integrating metallization, integrating light sources and drivers using selectively laser etched glass. We have built in some passive alignment. So we have some features that allow to drop in components and have optical coupling just by placing optical components. We are also including waveguides and having metallization, and we go into quantum computation system build-up. And this is an example of how glass can be used to create more modern assemblies for modern applications. Going into more quantum chip packages that can also be used in Hermetic and cryo operation, which is a big 0.4 glass. This assembly here is a quantum chip that had fibers adjusted in the package. This is an active alignment stack and package, and you can do the active alignment at room temperature. The later operation will be at hermetic and cryo operation, and the glass makes sure that you can go down to cold temperatures. There's another case that you have to have passive alignment. For example, if your light sources don't work at room temperature and you'd have to do the assembly at room temperature, then it's very advantageous to have features that can let you click together the optical system, so you can later put this into a cryo operation and have the single photon sources in this case operate. So this is a coupling of a special emitter chip with 40 micron pitch to a multi-core fiber, and you simply plug the optical fiber on top of the emitter chip as sketched here. Of course, you also want to seal packages, and this is where glass is also very advantageous. You can either directly seal glass and glass, or you can use some metal coatings, metal lines to have some metal glass interfaces. We do vacuum testing of these packages. We can also fill with gas, and that way our original sketch that we had at some point 10 years back, creating an optical system in thin glass, really took a more modern shape. It got flatter, yes, and we did hermetic packages, so we closed up the packages for hermetic operation. At some points, we not only use glass, we also have the capability to print optical elements into place. This is where we have two-photon polymerization, and we have a machine that can create photonic wire bonds. And the idea is to have to mount fibers and chips with relatively huge tolerances, and then go for the detection of the optical facets and print optical connection in 3D. This works surprisingly well. And another way to then couple with optics printed into place is, of course, the printing of micro-optical lenses or lens arrays. So these are examples that have been created on our two-photon printing machine. One has to make sure, however, that the two-photon printing is really only practical on small volumes, and that it is also not usable in extreme conditions like glass. So it's a very nice enhancement for glass packages, but it cannot be used on all glass-based systems. We just set up yet another laser machining process. This would be the so-called LIDE process, laser-induced deep etching. And this can create millions, virtually millions of holes in large glass panels at a rate of several thousands per second. And it can also create complex structures to mount optical elements and to enable passive alignment. We are currently setting up the machine, and we'll go into the full potential of this machine in the coming months. Of course, these through glass wires, if you structure them, also have to get metallized. We also have the machines available at IZM to do this, and are looking forward to make use of the full potential of this machine. So I would like to sum up passive versus active alignment. I hope I could show you some approaches, some limitations possibly, but some new perspectives in putting together optical systems. The core elements are glass interposers or glass cores. They are the base for future assemblies in, for example, optical chip or optical chiplet and quantum system coupling setups, for co-packaged optic approaches like in datacom and AI, and we can also do hermetic packaging for all types of optical sensing. We do this at wafer level and panel level, and we create mechanical, electrical, and optical coupling structures that are highly adaptable and scalable, which is the main advantage of laser structuring. We are in the lucky position to be able to select from both processes, SLE and LIDE, because we have both processes installed at IZM. So we are looking forward to combining the two, the one being a very fast and the one being the more accurate process. So we are creating mechanical and optical structures that are accurate in 3 dimensions, and that potentially enable passive alignment assembly approaches. The thermal conductivity in glass is not existing, but you can engineer it into the glass by filling through glass wires with metal, and this is what is a task in this approach. We can also integrate optical waveguides or print photonic wire bonds and microlenses where needed. Yeah, this is another way to enhance these glass packages. We have founded a glass panel technology group, and I would like also to refer to our next speaker, Julian Schwietering, who will go into more detail on this and who is going to talk about integrated photonics for the next generation of glass core substrates. With that, I would like to thank you for your attention and would be happy to accept any questions from you.